Okay, this is session 3 of computer-age statistical inference. Session 3, Fisher's compromise, which corresponds to CASI textbook chapters 4 to 5. Likelihood information and the parametric families that made 20th century statistics computable by hand. And slide 49 is about Ronald Fisher from 1890 to 1962. Dominated statistics between the wars, World War I, World War II, and left the method neither straightforwardly Bayesian or nor frequentist, and Efron and Hasty taste Fisherian. So, another term, Fisherian, as a third grade theme of classical inference. So his central instrument is the likelihood. For each candidate value of the unknown, how probable would the data we actually observed have been? So then his rule is that believe the value that makes your observation least surprising. So this is maximum likelihood estimation, the MLE, and it remains 90 years later the default method of most of science. Note the elegance of the evasion. Likelihood uses the Bayesian machinery of how well does each hypothesis predict the data, but stops before the prior and so incurs no philosophical debt. Efron and Hasty judge this compromise extraordinarily successful and quietly unstable, which is why the quarrel resumed in the computer age. Fisher as a character is worth 2 sentences. Fisher is fiercely combative, brilliant, responsible for both the best and the most misused ideas in the field. So, likelihood and maximum likelihood. The reverser is the southern part. Probability runs forward. Given the truth, what data should we expect? Likelihood runs backward. Given the data, how does each candidate truth score? So, an illustration with no mathematics. You hear a cough in the next room, a child or a large dog. You do not compute. You ask which hypothesis would more readily produce the sound. That is likelihood reasoning, and you do it hourly. Crucially, likelihood is not the probability of a hypothesis. A large L of theta, R of theta, does not mean theta is probably true. It just means theta would have predicted this well. Confusing the two is the Bayesian standing accusation against Fisher. So coherence or not, it works remarkably often, and the reason is chapter 4's next idea, Fisher's information. Fisher's information. Fisher information measures the curvature of the likelihood as its peak. A sharp spike means the data discriminates keenly between nearby hypotheses. A flat plateau means it barely discriminates at all. This yields the result that made the MLE, maximum likelihood estimation, the centrist default. In large samples, the MLE is approximately unbiased and attains the smallest variance any unbiased method could achieve, asymptotically the best possible instrument. Read the qualifiers carefully. In large samples, approximately, asymptotically. No, the guarantee is a promise about the limit, not about your actual study. So part 3 spends several chapters on what happens. Session 3 spends when those qualifiers fail. Many parameters, but small samples. Selective hypothesis. Okay, so 20th century guarantee has fine print, and 21st is reading the fine print. The fine print is a phrase to leave them with, review with. Okay, nothing in part 1 is wrong, but conditions under which it was proved are not the conditions of the modern data era. 52. Conditioning, permutation, and randomized experiments. So, conditioner inference. Conditioner inference. Judge your result against the circumstances that actually obtained. Not all circumstances that might have. If your instrument that day was the precise one, do not average your accuracy with the imprecise one you did not use. This sounds obviously right, and it quietly undermines strict frequentism, which averages over the whole hypothetical infinity Fisher's own students noticed. Now, permutation and randomization is Fisher's most beautiful idea and the most accessible one. To test whether a treatment did anything, shuffle the labels, pretend patient 3 got the placebo, patient 7 the drug, and recompute 3,000 times. If your real result sits comfortably inside the shuffled results, nothing detectable happened. If it sits far outside, something did. No formulas, no assumed distributions. So, computer-age method invented in 1935 by a man who had to do with cards. The tortoise hare thesis in reverse. Sometimes the idea waits these decades for the machine to catch up. So, permutation is the most intuitive idea in session 1. It's a direct ancestor of bootstrapping in session 7. Moving on to parametric models, the great compression. A parametric model says the whole pattern of variation in this data can be captured by a named mathematical shape and 2 or 3 numbers. So the normal distribution is only a center and a spread. So the payoff is enormous compression. Instead of 157 measurements, you carry 2 numbers, and all of a classical theory becomes available. So Alfron and Hastie surveyed the working vocabulary, univariate families for single measurements, the multivariate normal for several measurements that move together, the multinomial for counts falling onto categories. The unifying abstraction is the exponential family, a general form containing the normal, binomial, Poisson, and gamma as special cases, for which the mathematics can be done once instead of separately. So why care as humanities and social science majors? Because the edifice rests on a bed. The nature's variation belongs to a small catalog of shapes. When the bed holds, results are miraculously cheap. So part 3, session 3 is largely about what to do when it fails. So what the classical age achieved and what it assumed. Achieved was a complete coherent theory of evidence for a careful scientist with one clear question, a modest sample, and a pen. Not a small thing, one of the great intellectual constructions of the modern era. Assumed everywhere and individually that n is small and the question was chosen before the data arrived, that the parametric shape is right and the computation is expensive. Each of those 4 assumptions has now failed. Why? Data is fast in compute age. Questions are chosen after looking. Shapes are unknown, and computation is now nearly free. Therefore, Alphonse Hastie's judgment is generous and exact. Modern practice has vastly extended their reach without changing the basic outlines. They offer an analogy with classical and modern literature. The classics were not refuted by moderns but extended. So we cross over to next, where the machine arrives and extension begins. 55, maximum likelihood in a single picture. So you flip a coin 10 times and observe 7 heads. What is the coin's true propensity to land heads? The likely question for each candidate propensity, how probable was 7 heads in 10 under that value? So if the truth were 0.1, 7 heads would be almost impossible. If it were 0.5, 7 heads is possible but not especially expected. If it were 0.7, 7 heads is exactly what one would expect. If it were 0.95, 7 heads again is unlikely and you would expect 9 or 10. So plot the score against every candidate value and you get a hump peaking at 0.7. The maximum likelihood estimate is 0.7, which is simply 7 out of 10. Note that the shape of a hump tells you as well. With 10 flips, it is broad. The data barely distinguishes 0.6 from 0.8. But with 1,000 flips, it becomes a spike. That width is Fisher information, and it is where standard errors come from. The fine print made concrete. In large samples. With small samples, the maximum likelihood estimation can be noticeably biased. Okay. The maximum likelihood estimate of a variance, for instance, is systematically too small. So that's why textbooks quietly divided by n-1. For a fixed number of parameters, now when the number of unknowns grows with the sample size, the guarantees for fail outright. So this is precisely the situation of session 9's 6,033 genes, which you will see later. For a correctly specified model, the whole apparatus assumes the parametric family is right. If the true shape is not in your catalog, the MLA converges confidently to the best wrong answer. For a hypothesis fixed in advance, nothing in Fisher theory contemplates selecting the hypothesis after inspecting the data. So session 12 later is about to bill for that omission. So none of this makes maximum likelihood a bad method. It makes a method with stated conditions. And the most misuse consists of ignoring conditions that are printed in the manual. Next, a permutation test you could run with index cards. 12 students read a text. 6 are given a historical preface first. 6 are not. Comprehension scores are collected. The preface group's average is 4 points higher. So is 4 points more than shuffling would produce? Write all 12 scores on cards, deal them at random into 2 piles of 6, compute the difference of ages recorded. So repeat it 1,000 times. You now have 1,000 differences produced by chance alone from these exact 12 scores. If you observe 4 points sits inside the bulk of that distribution, say exceeded by 300 of the 1,000 shuffles, the preface did nothing detectable. It's only 8 shuffles exceeded, something happened. And 8 in 1,000 is your p-value computed from the first principles. So no distribution was assumed, no formula was concerted. The randomization in the design licensed the randomization in the analysis, which is why Fisher insisted the two go together. 58, a final guide to 4 shapes: normal, binomial, Poisson, and gamma distributions. So normal is the bell curve. Arises when many small independent influences add up: heights, measurement errors, sample averages. Its dominance is not an assumption about nature, but a theorem about averaging. Second, binomial, counts of successes in a fixed number of independent tries. 7 heads in 10 flips, 42 conversions in 200 visitors. Poisson, counts of rare events in a fixed window, when opportunities are many and each is unlikely. Insurance claims per year, typographical errors per page, arrivals per hour. Gamma distribution, waiting times and positive quantities with a long right tail. durations, income, sizes, used in later chapter to model the insurance prior. So these all four shapes belong to the exponential family, which is why one theory and one fitting algorithm serves them all. Recognizing which shape a question implies is the most of what applied modeling consists of. Okay, so questions for session 3. Number 1, likelihood asks which hypothesis best predicted the evidence. Is that how historical argument works? Give a case where it is and one that where it clearly is not. Number 2, design a permutation test for a question in your own field. What exactly would you shuffle and what does the shuffle assume? Number 3, all models are wrong, but some are useful. So name a model in your discipline that is wrong and indispensable and say the cost to use it. Number 4, Fisher's conditionality principle says, judge by what actually happened, not by what might have. Is that principle at work when we assess a historic actor's decision by the information they in fact had? So recap, 60, recap. What you know now is that likelihood is, in one sentence, is how well each candidate truth predicted the observed data. The common error is reading it as a probability of the hypothesis. MLE is candidate truth that predicted the data best. Error is forgetting its guarantees are asymptotic. Fisher information is how sharply the data distinguishes nearby hypotheses. Common error is ignoring that it depends on sample size. Now, conditional inference is the judge against the circumstances that actually obtained. Common error, averaging over experiments you did not run. Permutation test is shuffle the labels and see whether your results stand out. Common error is using it when the design had no randomization. Parametric model is a name, shape plus a few numbers. Forgetting the shape was chosen, not observed one, is a common error. Exponential family is a general form uniting normal, binomial, Poisson, and gamma. Common error, treating as a technicality rather than the reason theorems exist. So this probably the ending page for session 3. Yep. A reflection on models, the ideals, and the sin of mistaking the map. All models are wrong, but some are useful. This is a remark by George Box in 1976. A parametric model is deliberate simplification adopted because it's tractable. The danger is not that it is simplifies or thought simplifies, but that continued success attempts us to forget we chose it. Now, the Hebrew Bible's polemic against idols is not primarily about carved wood. It concerns the substitution of a manageable representation for an unmanageable and infinite reality, an object one can carry, address, and control. They have mouths, but they do not speak. Psalm 11, 115 and 5. It names a permanent temptation of the model builder. Now, Box's sentence is working form of the same wording and it keeps both helps. Wrong, so hold it loosely. Useful, so do not despise it. Refusing to model at all is not humility. It's another way of not looking. So discipline this session asks of you is name your model's assumptions aloud in advance in a form that could embarrass you later. So that's what chapter 5 does, and in part 1 remains honorable where it is now insufficient. All right, thank you very much.